So for some reason I thought I would get to vision today, but I realized there were some pieces of development and plasticity that I don't know if I didn't do them last semester. I don't know what happened, but we need to talk about the plasticity of the brain after brain damage. And so I'm going to back up a little bit here, talk about adolescence and old age, but then talk about what happens when we have damage to the brain. Your author goes through 2 times in life where he discusses brain development and then so really its effects on behavioral development. And we could do this throughout a lot of our infancy and toddlerhood as we're getting new motor skills and learning language and all of that. We are seeing brain development, but we could spend a whole semester talking about just that. Whereas picking these 2 times and choosing something to focus on is probably good. One is adolescence and the other is late adulthood. So if we look at adolescents, they are starting to develop the ability to perform the anti-saccade task at this age, which this is, if there's a moving target, if there's something like a flashing light over to our left, there's a really strong impulse to look at that flashing light. Okay, and what the anti-saccade task requires is that you move your eyes away from that target. So you are inhibiting that impulse, inhibiting that wrong response, similar to what we talked about with the Stroop task, only I feel like it's very much more low level. And what's helping us with this is the development of the dorsolateral prefrontal cortex. We see that adolescents are not equally impulsive in all situations, that part of what influences them is their social context. And so if we look at prefrontal cortex activity as an explanation for their behavior, it doesn't explain it very well, because what happens during adolescence is it becomes more and more and more likely that they're going to have some risky behaviors. But what's happening with the prefrontal cortex is it is developing over that time, and so it should be becoming, over adolescence, somewhat less likely that they have these risky behaviors if it's just explained by prefrontal cortex activity alone. So another thing we have to take into account is this processing of rewards. And apparently for adolescents, that part of the brain, those more subcortical structures, the reward pathway, I usually go a little bit into the limbic system being developed and hormones as well, but just looking at the reward pathway, that is what's important to them is this anticipation of rewards, and particularly in specific social contexts. So when they are around their friends and trying to fit in, and that reward of fitting in really is very important to adolescents. The other time he talks about is old age, although some of this starts pretty young. So the volume of the hippocampus begins to decline. The frontal cortex begins to thin at age 30. So some of this is really beginning in our young adulthood. People who are older usually make their decisions more slowly. But all of this is important. These are important things that we see as people age, but they're really based on averages across many different people in many different walks of life, some of whom are kind of allowing themselves to atrophy in some ways, especially if we have the kind of job that is not intellectually stimulating and challenging to us, and also we aren't doing our aerobic activity and staying active, we are more likely to see greater amounts of this. Whereas people who are in these jobs that are creating some challenge, that they are constantly being stimulated and are also continuing their different kinds of strength exercises, aerobic exercises, we're going to see a lot less of this. So these are really based on averages. And we also see, so I like to stick up for older adults quite a bit, one, because I'm becoming one, but also because of, if I look at my previous generations and like my grandparents and now my mom, as they get older, they have more chance to have like wisdom, because they have this greater knowledge base. They have more experience over more different kinds of experiences, and they have found ways to compensate for these various losses of brain anatomy or brain activity so I make decisions more slowly, and instead of using, it sounds like to me, one part of the brain to make that decision, just as an example, I might use several brain regions as a way to compensate for that specific change in brain anatomy or brain activity. The next module of the book is talking about plasticity after some kind of brain damage. Callett very briefly goes through some possible causes of brain damage. This can happen throughout our lives to things because of things like tumors, infections, some kind of exposure to toxins, drugs, radiation, neurodegenerative conditions that we will talk about. Alzheimer's, we'll talk about Alzheimer's when we talk about memory, and Parkinson's, we'll talk about Parkinson's when we talk about movement disorders, but it's also going to be mentioned in the memory chapter. For young people, so for people your age, the most common cause of brain damage is some kind of closed head injury. And how much damage, I mean, a lot of people obtain some kind of blow to the head, mild blow to the head at some point in their lives as we're children and we're young and we're impulsive. This is really quite common, but how much damage that's going to do, it really depends on the severity and then the frequency. How often are these blows to the head happening? And most of the damage is from that kind of I don't want to say centrifugal force, that kind of everything is moving, and then when the moving stops, the parts of the brain are hitting the skull, and those neurons are getting damaged. But there's also sometimes some blood clotting that is causing some damage. And I can't remember the statistics exactly of about maybe 2 or 3 per 1,000 people have some kind of real more long-term problems from damage. If someone's at the time of damage experiencing some confusion or memory loss, and especially if it's both, that's more likely to cause more long-term damage than if those things don't occur. But that's as much as I can say about the prediction of that, because a lot of people have small injuries to the head in their lifetime. As we get older, it becomes more and more likely that we're going to have some kind of stroke. So your author goes through different kinds of strokes for a little while and what this can mean as far as brain damage. There are different kinds of strokes that happen. So the most common kind of stroke is an ischemic stroke or ischemia, where there's some kind of blood clot or other obstruction such that neurons beyond that clot or obstruction are not receiving the oxygen and glucose and so forth, and so that can kill some of those neurons. What is much less common is a hemorrhage, which is the result of a ruptured artery, and this is causing just this flood of the blood into a particular area, and that's going to give excess oxygen, excess calcium, other chemicals. So if you remember talking about causing an excitotoxic lesion on animals when we're working with animals, this is what's happening in a hemorrhage. Is there's overexcitation, and those neurons can die that way. Regardless of whether it's an ischemic stroke or a hemorrhage, there can be some edema, so this accumulation of fluid in the brain, and that's going to increase pressure on the brain wherever that accumulation is occurring, and that actually increases the likelihood or probability of additional strokes in that area. Something that's really important about knowing what to do in a stroke, if someone's having a stroke or if you think you're having a stroke, is you can immediately think about this FAST acronym that is super helpful, regardless, again, whether it's happening to you or you're watching someone else. FAST stands for facial weakness or facial drooping. A stands for arm weakness, or you can ask them if they have some arm weakness. S stands for speech problems or slurred speech. And T stands for time. Time is very important, the time to call 911 or the time to get that person to a hospital. I have known somebody who had a stroke, and one of the problems is if we're not educated about what's happening to us, we might not behave quickly enough, and so time lost is brain lost. And I know this person, he at the time he pooped himself, and he wasn't at home, and he didn't know what was happening, and so he went home to change his pants because he was embarrassed. And really, it's okay to be embarrassed. Embarrassment is better than losing any aspect of normal brain functioning in my mind. So one of the immediate treatments that they often do for people who are having a stroke is this TPA, this tissue plasminogen activator, which is going to go and break up the blood clots. Now, if this is an ischemic stroke, which remember is much more common, this is going to be very helpful. And I have this picture over there. I just really put it there so I'd have more pictures on my slides, but you can see in that first part the kind of breaking up of the blood clot. But this has to happen really quite quickly. This needs to happen within 4.5 hours of having a stroke, and the sooner the better, because again, if you're blocking that area, there's more likely to have more edema, more possibility of other strokes or additional strokes in those areas where there's fluid buildup. Other things they've tried, I did not go back and look through these because all of this has been, from what I remember of reading this before, all of this has been conducted on animals, and some of it is more promising than others, but none of it has reached this kind of human trials where it seems like these are actual real treatments. But we might try blocking glutamate synapses, as that is in hemorrhage or when there's edema, what's happening with that fluid buildup and so forth is the oxygen, the glucose, and really the glutamate. Remember, that's the excitotoxic lesions that we were causing in the animals, was with glutamate, so we're overstimulating. So we might block those synapses. They might block calcium entry, since we're getting more chemicals into those neurons through that calcium entry as part of it. They sometimes try cooling the brain. And then they also have tried exposure to cannabinoids, and that's one of the more interesting kinds of tactics. What they've done with, I think this was rats. I can't remember if it was rats or mice. I apologize. I'm going to do that almost every time. Where they expose them to cannabinoids right after a stroke, and your author has some really interesting pictures of how much less damage there was in those animals. What appears to help even more is exposure to cannabinoids before the stroke. So of course they're inducing strokes in these animals, and so they can control that. But normally, that's not something we can normally do, is think, oh, I might have a stroke, so maybe I should expose myself to some cannabinoids. But they do appear to help the animals and having less brain damage. And finally, I have this picture that comes from the book. You can see in A, this is the brain of a person who died immediately after a stroke, and you can really see the swelling on the right side, or actually I'm assuming the brain's flipped upside down to the left side. And then the brain of someone B is in the brain of someone who survived a stroke for a long time, and you can see that there has been some brain loss as the ventricles are enlarged. And there are just some areas where you can see these more formed kind of sulci in the brain of neural loss. And C is a person who suffered a gunshot wound and died right away. And so I wish your author said a little bit more about this. It's not really as relevant for what he's talking about with the strokes. And I guess it's just a comparison, but I don't really, that strip of necrosis in the brain, I've never seen that kind of pattern of necrosis, but that's someone who died immediately after being shot in the head. And you can see where they were shot. Some of the later mechanisms of recovery, so we have those immediate treatments, but after damage occurs, we're going to see a lot of reorganization of activity of the brain, increasing activity in different areas. Sometimes one area is going to basically take over the function of a damaged area as the damaged area isn't working anymore. It really depends on what's damaged and what the regions close to it can do, or the regions that are in the same pathway, whether or not they can take that over. Other times we see some compensation where we are just using different brain pathways in order to compensate for some brain damage. Another important term to understand is diascasis. So this disruption that we can see to really kind of distal brain regions that because they receive decreased activity because some of the neurons that we're communicating to those are damaged, if that's coming out a little bit like I try to say it there. But so some of the behavioral deficits that we see after a stroke are reflecting really more than just the neurons in that area that have died, because other areas have lost their input. And I have here, so as we're looking at later mechanisms of recovery, one of the things they have discovered is that they might go in and stimulate a particular area of the brain. And this study by Schiff et al. Talks about a man who was in a minimally conscious state for 6 years, and then they go in and they give him some brain stimulation to his central thalamus and found substantial improvements, including his self-feeding and some intelligible speech. So that looks like that could be helping, especially some of this diascasis and stimulation to those areas that were receiving information from neurons that are now damaged. Really related to this kind of brain stimulation, they have also looked at stimulant drugs, because this is just stimulation in a different way, right? So the stimulant drugs would be dopamine agonists. Feeney and colleagues in several studies have looked at rats and cats that they have induced some kind of cortical damage, and specifically to areas that are responding to movement perception and depth perception. And if they gave them these dopamine agonists, so a stimulant drug, and they had those animals perform those behaviors, so receive movement information and practice at movement perception, basically, and depth perception, then they could see long-term improvement. They also found that if they had a dopamine blocking drug, that this would impair behavioral recovery, which just makes sense as the flip side of that coin. If we see some kind of damage that has destroyed some certain neurons or cell bodies, those cell bodies are not going to be replaced. But damaged axons can grow back under certain circumstances. This is something I mentioned really early as we were talking about the glial cells, that in the central nervous system of mammals, this is really unlikely. I think they're doing some pretty exciting research with rats and mice right now, but what's happening in the mammalian central nervous system is those astrocytes get in there. They are going to release chemicals that are going to cause axonal sprouting right where that astrocyte is. They also go into where there is damage, and they create this kind of scar tissue, and so the axon can't, basically, I usually use my hands a lot here, but the axon can't go around that scar tissue, and it's releasing these chemicals, so it just does this kind of axonal sprouting right there. So it can't really get back to its target a lot of the times. We do see, however, regrowth of axons in the peripheral nervous system of mammals. So even if an axon is crushed, that axon is going to grow back at about 1 millimeter per day by following that myelin sheath, by following those Schwann cells, so that it can go and find its original target. Targets. I'm a bit behind, and so I'm going through these concepts a little bit faster, and I'm leaving out a lot of the complications. I usually do these two things and maybe 2 or 3 slides along with the previous slide. This all takes a while usually. But so other mechanisms of recovery. So these have some complications that you might want to go read about in your book if you're interested at all in this kind of recovery after brain damage, of what's happening naturally in the brain. One is we have axonal sprouting, which I was just referring to before. If it's happening where I can't get to my intended targets, or it's happening where I'm communicating to a brain region that does something different, really different than what I'm doing, then axonal sprouting is not helping. But sometimes if I'm still being able to communicate, so I've lost a couple of axons to a target, and then I have other neurons doing something similar. They have axons going to that target, and we see this, either I have some axonal sprouting or they do, then we can see a real benefit of that kind of increase in input. So after we lose input from an axon, that postsynaptic neuron is going to release some neurotrophins, inducing other axons and strengthening those synapses so that those axonal sprouts, that we see these branches and that they are successful synapses. Another thing we see that can help, and again, both of these have complications where they can hurt us as well. But another thing that can help is denervation supersensitivity, or really the supersensitivity of the receptors of the receiving neuron. So if I'm the receiving neuron and I'm losing my axons or input to an area, then my dendritic receptors I'm starting to become more sensitive to the input that I am still receiving. And I went through those quickly because I really still wanted to keep in. This is one of I find this really fascinating, this kind of reorganization that we see. And so how we can see these kind of phantom limbs that people experience, that this is a reorganization of the somatosensory cortex and the motor cortex too. We might feel like we're moving these limbs, and that can happen. As we have, if we look at the picture on the left in A, we have a normal hand there, and then you can see the kind of brain representation of that hand. And we haven't really talked about this because we haven't done sensation and perception yet, but each of those digits has some representation in the brain, and then you're seeing some representation of the palm near those digits as well. And that's just where we are in the brain in there. And then so if we lose a finger, we still have that region of the brain that wants to be active, that's going to be active, and that representation can mean that the fingers around it get more representation, that palm area has more representation. And so when I'm getting touched, let's say now on my index finger, it can feel like it's happening in my middle finger, because that was the region of the brain that was representing my middle finger. So I might still feel that as being there. This is basically repeating the slide before, except now showing what this can mean as far as how this representation, what the outcomes are for somebody who's maybe lost their arm. And so we're looking at the somatosensory cortex in A of the picture on the left, and you can see that the arm and hand are close to the upper arm on one side and close to the face on the other side. And so if I've lost my arm, that brain region, it still wants to be active, and it's still, those neurons that are close to that are going to have some probably axonal sprouting, and they're going to start communicating to that region. And that was where the arm was. So if this person is being touched on the shoulder, they can feel that in parts of their digits. So the 1, 2, 3, and 5, as we saw on the page before. If they're touched on their face, they can feel that on different digits as well. And so that those digits are lost, but they're still feeling them, as that part of the brain is still active and just receiving information from different areas of the body. There are also just learned adjustments in behavior. So it really helps to practice skills that are impaired but not lost. So using those brain regions that are probably experiencing some diascasis and compensating in the brain for regions that are lost. For a neuropsychologist, this gets really tricky because they need to figure out what is the impairment to have the person practice the appropriate skills. So if a person, just for example, is having problems following spoken instructions, as a neuropsychologist, as someone who's trying to help them, It's difficult to tell whether this is a problem with hearing, a problem with memory, a problem with their language skills, motor control, alertness. All of these are possibilities, and we need to figure out what is actually going on. And all of this needs to be done as soon as possible. Again, time lost, even at this later, these later kind of mechanisms of recovery, time lost is brain lost, and the faster we can get the different regions of the brain to rewire or to get some kind of stimulation, practicing those skills is really important. I've given myself less than a minute for my summary slide here, but I did want to have it in here as it is Friday, and I will see you guys on Monday. I can't wait to see you all again. I've missed you last week. But we have discussed neural development, starting with embryological kind of development, but then continuing on and before, even till a little bit after we're born, of seeing some of the proliferation, migration, differentiation, synaptogenesis, and myelination. We talked about axon finding and how that happens during neural development. We also did this fine-tuning by experience, so experience-dependent brain plasticity. I get pretty excited about that a couple of more times, I'm pretty sure. And then that little tiny snippet of development during adolescence and late adulthood. Again, we could have spent a long time on different areas and times of our lives. There's a lot more going on during those times, but that was just a little snippet of a couple of times of development in later life. And then the plasticity that we see after some kind of brain damage and the changes that we can see, different mechanisms of recovery, both immediate and later. So again, it is Friday. I hope everyone's doing well. Take care, stay safe. Can't wait to see you. Yeah.